Good evening, everybody. Welcome to the talk, The Art of DSP in Reactor. Thank you for coming. The talk will take approximately 1 hour, and then we're going to have a Q&A session. I would like to begin the talk with a short demonstration. So the field of music DSP concerns itself with a large number of different signal processing and generation algorithms. And some of them you can see here on this slide. And one of the larger areas of this field is the filter design. You can find filters in synthesizers, like synthesizer filters, equalizers are filters, and the filters are also used inside various effects, blocks, and what have you. So they're very, very common. And I would like to demonstrate to you a particular filter sound in the beginning. So what you just have heard, it's basically a static setup. There is just a sawtooth oscillator going through a filter with no audio FM or any crazy stuff going on. This is the basic sound of the filter. And are we hearing feedback? Yeah. And I hope you will agree that the filter sounds somewhat remarkable. So it's quite special. And I would like today to tell you a story of how this filter was developed. The filter was developed in Reactor. Reactor is software by Native Instruments. This is what you see here. So this is Reactor. And basically, if you ask someone what is Reactor, you could get a number of different answers. And the two most common answers probably would be saying Reactor is a modular synth or Reactor is an instrument effects creation platform. And these are just two different angles how you can look at Reactor. So if you look at the screen here, then below you see some kind of modular structure. So these rectangles are modules which are connected by wires. It's pretty familiar module paradigm. Although these blocks are on a somewhat lower level than in a hardware modular. For one, they don't have a built-in panel in the same sense as hardware modular blocks do. And instead, you can construct custom panels separately. So here above, I'm having the respective panel. So this is like a small instrument or the setup which I have prepared for the demonstration. And you can prepare much more complicated setups. You can build whole instruments, and Native Instruments also releases a whole line of products, instruments and effects built in Reactor. And there is a large number made by third parties, also freely available in Reactor user library. So this is approximately what Reactor is. And I would like to mention there are two different levels in Reactor. One is the so-called primary. This is what you see here. And one is REAKTOR Core. So these modules here are not atomic. They have internal structures, and I can double-click this module. For example, this is an oscillator. I can double-click it, and I'm diving inside. This is the internal structure of this module. And it looks a bit different. That's because it's a different layer of Reactor, this so-called REAKTOR Core. And it's using the same modular paradigm. So again, you're connecting different modules by wires, but it's quite different on the conceptual level. It has different event model and lots of other small differences, which in the big picture become like really significant. And one of the main focuses of REAKTOR Core is construction of custom DSP algorithms. So in this case, we're having here an oscillator. And actually, this block here is the oscillator itself. It has, again, an internal structure, which you can see if I double-click. I can go inside. So this module is referred to as a core macro, which means it's not a fundamental module. And this is also a core macro. I can double-click. And this is a macro I can double-click. And this is a macro I can double-click. And at some point, I can't double-click anymore. So these two modules are fundamental. They're like read-write operations, and there are other fundamental modules like multiplication, subtraction, addition. So you really start with a very low level, and then you can construct a large variety of DSP algorithms in REAKTOR Core. And Of course, we don't just release Reactor as It's an empty platform for our users. It comes with a library of pre-built core macros, and among these macros is stuff like this. We have pre-built oscillators, pre-built filters, and so on. And this serves dual purpose. On one hand, of course, not everybody of our users is a DSP expert willing to build custom DSP algorithms, and this is some kind of content which you can start right away with. And on the other hand, for those who wish to use REAKTOR Core as a DSP construction tool, this provides some kind of starting point. You can look inside, see how the things are done, and this can just be an example for you. This is how you can do DSP in REAKTOR Core, not how you have to do it. It's a completely open and free thing, but this is how you can do it at least. And we just about to release, I think it will happen in the next few days. It's not yet out, a macro library update, so this will be a new version of REAKTOR. As we're filming this, I think if you're seeing this on video, this version should be already out. And the update contains a large number of additions to the core macro library. And again, I'm approximately listing the content here on this slide. And a big part of this update are new filters, including the filter which I have demonstrated to you in the beginning. And as I mentioned, this will be the subject of our today's talk. The talk will be on a qualitative level. I will not go deep into the DSP math. If you're interested in mathematical side of what we will be talking about today, I can recommend you to refer to the new revision of the book, The Art of VA Filter Design, which just has been released about a couple of weeks ago, I think. You have to be careful to download the latest version, which is revision 2.0 alpha. It's freely available from Native Instruments website. You can find it in REAKTOR area of the website. Or you can just Google for the name, but then you have to be a little bit careful. You could look for the latest changes on the web or specify the version, because I think mostly Google will still give you the previous version, which is 1.1.1. So you just have to be insisting for Google and ask for the latest revision. So the talk itself will not go deep into the math, but I hope it will be interesting both for people who are not too into the math side of the DSP, but simultaneously for those who are into the math side, because it will be basically about thoughts about decision making, and math is just some kind of detail, which is just a helper tool. It's not critical in that sense. So let's begin with the story. The story began with our desire, which we spontaneously had when we were working on the macro library, to construct an 8-pole low-pass ladder filter. We already had a bunch of 4-pole ladder filters, starting with a 4-pole low-pass ladder filter. The term might not ring bells with some of you, and with some of you probably does, but maybe some other term will. Moog VCF or Moog Filter essentially is an implementation of kind of abstract technical idea, which is a ladder filter. And it's shown in this picture approximately. This is a block diagram which describes the idea behind the Moog ladder filter in like the basic form. What we're having is a serial connection of 4 one-pole low-pass filters here, these blocks. And then we're having a negative feedback around these filters. And this triangle is a gain element that just multiplies the signal by some value k. So by varying this variable k, we can control the amount of the feedback. So this minus negative feedback just means that the feedback is inverted. It multiplies the signal by -1 here. This is the basic idea of a 4-pole low-pass ladder filter, which we already had in our library. And I would like to mention that what we're having in our library are not exact models of analog prototypes, so we were not attempting to specifically model a Moog filter, because there are lots of details which you can refine further and further to high degree of precision, but this is not the purpose of our library. The library tries to implement some kind of standard or generic technical ideas which we refer to as bread and butter. And in that sense, we're having a bread and butter ladder filter in our library, which I'm now going to show to you. Maybe first I just play the sound. I think it's going to be a bit loud. So this is the filter without resonance. And I can increase the resonance amount. And maybe those of you who are familiar with the sound of the Moog filter can agree, well, this is not an exact model as I mentioned, but it has some basic qualities of the Moog filter sound. This is the model, and now I'm going to show to you how it's made in Reactor. So it's currently this block which is being active. And this is a structure built in REAKTOR Core. I will delete these outputs because these are model outputs which we don't care about for now. So this is pretty much the same structure which we have seen in this picture. So we're having 4 one-pole low-pass ladder filters. The connecting wires are doubled, but that's a technicality of the ZDF toolkit, which is used to build these filters, which is again a toolkit consisting of macros. But I'm not going to go into details of this toolkit. So what we're interested in about today is that we're having a series of 4 one-pole low passes. And we're having this feedback gain element, the same triangle which we had here. And this is a negative feedback block. And that's how you build a basic linear 4-pole low-pass ladder filter in REAKTOR Core. Very straightforward. And I just showed you how it sounds. And here on the spectroscope, you can see the measured amplitude response of the filter. So the trick is that actually I'm having 2 identical filters running in parallel, and one was receiving the sawtooth signal, this is what you heard, and there is another one which is receiving white noise signal, and there is a spectroscope at its output, and it's kind of measuring the amplitude response of the filter. So far so good, and now we decided that we want to try to build an 8-pole ladder filter. So 8-pole ladders are not as common. 4-pole ladders are very common in hardware. They exist in many different places. 8 poles are somewhat rare, but they are out there, both in analog form and in digital form. Again, we didn't try to build a particular model of a particular hardware piece. We just wanted to implement some bread and butter 8-pole ladder filter. So how do we do it? Actually, sorry, I forgot to explain a bit about the 4-pole ladder filter because it will become important when I speak about 8-pole low-pass ladder filter. I wanted to explain at which frequency we're getting this resonance peak and how much of the feedback we need to get this resonance peak, because this is something which will be different with the 8-pole, and I would like you to understand why this is happening. So this resonance knob is actually scaled. Internally, when the resonance is set to 1, the amount of feedback will be set to 4. So this feedback coefficient will be equal to 4. The resonance knob is multiplied by 4 internally. And further, it's also clipped, not the knob itself, but the value which is coming into this gain element is clipped a little bit below 4. Why is that? Because at 4, the filter will explode. The resonance peak becomes infinitely high at this value, and the output level of the filter will grow indefinitely, and basically this is what we refer to as explosion of the filter, when I actually don't want this. That's why this filter internally clips the amount of the feedback to a lower value. And I would like to explain kind of the mechanisms behind this feedback, this resonance or self-oscillation, as we say, this infinite resonance occurring at the feedback amount equal to 4. And the fact that it occurs at the cutoff frequency of these 1-poles. So this cutoff knob controls the cutoffs of these 1-pole filters. And it's exactly this frequency, this cutoff frequency, where the resonance peak is occurring. So why is that happening? It turns out that the infinite resonance peak, so exactly infinite height of the resonance peak, or the self-oscillation point of such feedback structure, occurs at a frequency where the total phase shift across the this feedback loop will be 0 degrees, and the total amplitude change across this loop will be exactly 1. So basically, it will occur when a signal at some frequency is coming exactly unchanged through this feedback loop, and then we're getting infinitely high resonance peak at this frequency, and this is a self-oscillation. So let's find out where this is happening. On this slide, I'm showing to you the amplitude and phase responses of a one-pole low pass. So of each of these blocks here, these are one-pole low passes. Please ignore the dashed curves. Just to concentrate on the solid ones. So this is the amplitude response of a one-pole low pass. And this is the cutoff frequency. And you can see that to the left of the cutoff, it almost doesn't change the amplitude response. It's like 0 decibel change. Then at the cutoff frequency, it drops the amplitude of the signal by approximately -3 decibel. So if you send in a sinusoidal signal into a low-pass filter at the cutoff frequency, at the output, its level will drop by approximately -3 decibel. And further to the right of the cutoff, it drops even further. And here it's like 3 octaves above the cutoff. You get a drop of approximately -18 decibel. So this is a low-pass filter. But the filters do not only change the amplitude of the signal, they also change the phase of the signals which are going through them. And here we're having the phase response of the same filter. It tells by how many degrees, or like this is actually in radians, the phase of a sinusoidal signal which comes at the infilter's input will be shifted at the output. So again, the low frequencies, which are much smaller than the cutoff, will be almost not shifted. At the cutoff, we're getting a shift by -pi divided by 4, so -45 degrees phase shift. And to the right of the cutoff, the phase shift increases, and we're getting -90 degrees, like almost. So the peak, which we see here, occurs exactly at the cutoff. And let's now see that this is indeed the case from just what I explained. So at the cutoff, each of the one poles contributes a -45 degrees phase shift. This means that 4 of them will contribute a -180 degrees phase shift. And now we're also having an inverter here, which gives us another 180 degrees phase shift. So in total, it's 360 degrees or 0 degrees phase shift. So the signal phase is unchanged at this frequency when it goes through this loop. But its amplitude is dropped because each of the one poles drops it by approximately -3 decibel. So 4 of these will drop the amplitude by -12 decibel approximately, or actually exactly 4 times. This is the value which you can compute mathematically. This is actually the first time when you need some kind of math thinking about this. Everything else is mostly qualitative, and now want to compute the amplitude response drop at the cutoff. This is where we need the DSP theory. So we get a 4 times amplitude drop at the cutoff frequency here. So we need to compensate it, and if k is equal to 4, the amplitude will be unchanged across the feedback loop. So the phase is unchanged, we have 0 degrees phase shift, the amplitude is unchanged, and this is where we're getting infinitely high resonance peak, the self-oscillation. One could think about this on an intuitive level. It's not like really correct way to think of things, but I think it's a nice parallel that you think the signal enters the feedback loop, goes through it, enters it again unchanged, so it's added to itself at this point, goes again through it, enters it again unchanged, and does so infinitely many times. And that's why the signal level becomes infinitely high. And if k was less than 4, then the signal would still have the same 0 degrees phase shift, but slightly smaller amplitude. And it's like a geometric series sum. And you hopefully remember from school that you can have infinite geometric series, and if its denominator is smaller than 1, then you're having a finite sum of this infinite series, so the resonance peak will not be infinite. And this is basically the idea. And this is why we're having this resonance peak here appearing exactly at the cutoff frequency. So this is the basic theory behind the 4-pole ladder filter. And now we want to turn it into an 8-pole ladder filter. How do we do it? I guess everybody could guess by now. We just want 4 more of these 1-poles, and this will give us an 8-pole ladder. And this is indeed what we have done. I can show to you the structure. So this is an 8-pole ladder, which we did. Again, I will kill the model outputs, which are cluttering the view. And now you can see we're just having 8 instead of 4 of these one poles. And this is almost it. I will demonstrate to you the sound for now. So this is without resonance. 4-pole, 8-pole. Actually, the biggest difference in sound is due to the cutoff compensation. I will explain to you later. So it's actually having strong roll-off, but doesn't sound much different. I can increase the resonance. So I think now you can hear some difference in the sound. And this is just a linear filter. So hopefully we'll get a bit more difference in non-linear version. But that was the linear version for now. This is how it sounds. So a bit different. So besides just adding 4 extra one poles, we had to do a couple of additional changes to this filter. And that's because if we just add 4 one poles, then we'll notice 2 things. For one, the filter will enter the self-oscillation, the infinite high resonance peak, much sooner than the 4-pole. Actually, it will start self-oscillating at the feedback amount approximately 1.88 rather than 4. And the peak will also occur at a lower frequency than the cutoff or than the peak of the 4-pole. And now we should be in a position to realize why that is happening. So at the cutoff, now we're having 8 of these filters instead of 4. So instead of minus 180 degrees phase shift from the 4 one-poles, we get 360 degrees phase shift from the 4 one-poles. And then we're having additionally this inversion, and that's like 180 degrees total phase shift. So no resonance peak at the cutoff occurring. One could ask, okay, why don't we then remove the inversion here? We could have the positive feedback. Not a very good idea, because we also have a 0 degrees phase shift at very low frequencies. And then we would have kind of resonance at DC, or like there would be a very large amplitude boost at the low frequencies. We don't want this happening. This is not very interesting. So we keep the feedback inverted. But then the resonance peak will occur not where the phase response is 45 degrees, but where it's like 22.5 degrees, 1/2 of that. And then from the 8 filters, we're again having 180 degrees phase shift, and there is inversion, having 0 degrees total phase shift. So the resonance peak will occur approximately at this frequency. And it's already compensated in the filter which we built, so the resonance peak was occurring at the very same frequency, but that's because we already kind of take this into account. This was one change which we did in the 8-pole low-pass ladder. And also, if we look here, then at this frequency, the amplitude response drop is much smaller. It's even not 1.5 decibel, it's even not half of this, it's much smaller, which means that we need the feedback gain to be much smaller when the filter self-oscillates. And again, we can get into the math and compute this value exactly. Its approximate value is 1.88. This is the scaling value which we use for the resonance knob. So this is what we're doing on this level. You can see here that the resonance knob is multiplied by 1.88, and you can see that the cutoff frequency is multiplied by 2.4142. These are the compensations which we did because the resonance is not happening anymore at the cutoff, and that we need a different scaling for the resonance. And I hope this is pretty clear by now why we did that. So that was the first step. We did the linear version of the 8-pole ladder filter. But in analog world, the filters are nonlinear. And you're having very different nonlinear effects, and the most common one, most prominent one, is the saturation. That's because the signals can't get infinitely large in analog world. A current can't get very large, a voltage can't get very large because they're limited by the power supply at least, or there can be other reasons for saturating the signals. So the signal tries to get larger, but it can't because power supplies can't really drive it enough. And we refer this as a saturation. So it's not a hard clipping. It's not that the signal tries to grow to some level and then it doesn't grow any further, not necessarily like that. It can just saturate smoothly, so to speak. And we are emulating some of these effects in digital world. So in digital world, we have to implement them manually. They're not occurring for granted. By default, the filters are linear. And there are lots of different ways how you can implement these non-linearities. We can also look for like trying to get close to particular hardware units, or we can implement this in a more generic theoretical way. And one of the simplest generic way is basic feedback saturation, which is shown in this picture. So it's the same ladder filter, and we have 4 one-pole low passes here. And we put a saturator into the feedback loop. 10H stands for hyperbolic tangent. This is one function which is like very useful, like saturator. Doesn't have to be exactly this function, can be some other. But this one is pretty common. And we can just put it into the feedback loop. And among other effects, this thing will allow the filter to go really into the self-oscillation. We can grow the feedback amount above 4. And the filter will not explode because the saturator will prevent it from doing so. And we can explore the self-oscillation range of the filter. Again, I will now show it to you with the 4 poles. So this is the same thing done in REAKTOR Core. Let's kill these outputs. You can also ignore these modules. This is a slightly more complicated feedback structure because we're having extra functionality in our library for nonlinear filters, but it's currently not active. So essentially, it's the same gain element in the feedback. And there is the saturator in the in front of the series of the one poles. So again, very straightforward. The same structure which we have as a block diagram here, and it's just done in REAKTOR Core. And now we can listen to how it sounds. I'll actually start with a small drive because there's one effect which I would like to show to you. So now the filter produces some sound even in the absence of the input signal. So actually now there is some small input signal, but even if there is no input signal, the filter will still continue ringing. This is referred to as self-oscillation. So the resonance tries to grow infinitely, but it can't because of the saturator. And now I will add more of the input signal. And you can hear that there is some range, or maybe I'll try a slightly different cutoff. There is some range where the signal is like vibrating, it's getting a bit more complicated. And then when I increase the signal level above that range, this ringing almost disappears, and we almost don't hear the resonance. There is some resonance, but we mostly hear the input signal. So there is this kind of sweet spot if we're looking for this complicated signal. And there is an explanation for this sweet spot, which is on qualitative level, especially because it's quite difficult to analyze the behavior of nonlinear filters. We're having a limited headroom of the saturator. And first, this headroom was used almost exclusively by the resonance of the filter. And then we're adding more and more of the input signal, and the input signal also wants some of this headroom for itself, so it's kind of pushing the resonance out of the headroom. But if the input signal is not too strong, it doesn't really win over the resonance, because then the next moment the resonance pushes it back, say kind of, no, I want to take the headroom, no, I want to take the headroom. And they're fighting with each other, and this is probably responsible for this complicated sound. I don't have proof for this, but the explanation sounds pretty plausible to me. This effect will be interesting for us also later in this lecture. So this was one type of a nonlinearity. There are other types which I would like to mention. One I'm referring to as transistor-style nonlinearity. This is a model of the most prominent nonlinear effect happening in the Moog filter, which is based on transistors. And in this case, the saturator is not just like that in the feedback loop, so nonlinearities is happening are happening within the one poles, because the one poles are based on transistors, and transistors contribute this nonlinear behavior there. There are also other versions of the ladder filter which are not built of transistors, but for example of operational transconductance amplifiers. And they contribute other nonlinear effects. And again, there is one particular nonlinear effect which we thought is interesting, which is generated by the OTAs, operational transconductance amplifiers. And we're also emulating that effect. Again, happens inside these low passes. I'll just show to you the sounds in comparison. So this was the simple feedback saturator. And this is a transistor ladder. So it's not an exact model, but this is the most prominent nonlinear part of the transistor nonlinearities. And this is one particular aspect of the OTA nonlinearities. So this sounds somewhat different. And this is far in the self-oscillation range. Everything you can see, the resonance is set to 2, self-oscillation is happening to 1, so it's kind of double the self-oscillating feedback amount. This is where we're getting some of the most interesting virtual analog sounds. And of course, we also wanted to have the same for the 8-pole low pass, and we did, and the extension is pretty similar again. So, for example, I will show you for the OTA. This is the OTA ladder structure, 4-pole one. And the difference is that these 1 poles are nonlinear. They're having slightly different structure internally, and they generate OTA style of nonlinearities inside. And then you turn this into an 8-pole just by adding 4 more of these. And again, I'll give you a short demonstration. So this was like the 4-pole. This is the 8-pole. So maybe we want some kind of smaller drive for this complicated sweet spot. So this is the OTA. This is transistor ladder in comparison. So kind of different nonlinear effects. So far we were pretty happy and kind of achieved our very first goal. And then we thought, okay, we're also having high pass and band pass 4-pole ladder filters, which we also wanted to have originally in the library. And then we thought, okay, we can also make 8-pole versions of those. I will quickly talk about the high pass. So how do you make a high pass ladder? You just replace all 1-pole low passes with 1-pole high passes. And then the rest is very much the same. You just get symmetric amplitude response. It's a high pass instead of low pass. Not much to talk about. The band pass is much more similar. Oops, sorry, spoiler. So how are we making a band pass ladder? So low pass was made out of 1-pole low passes. The band pass was made out of 1-pole high passes. And the band pass needs to be made out of 1-pole band passes. Okay, so some people are already laughing because they know there is no 1-pole band passes. Band pass needs to have at least 2 poles. Well, not a big problem. What we do is this. So we replace only half of the low passes with high passes. So each of these pairs will make a 2-pole band pass, low pass, high pass pair. The amplitude response of this pair will look like this. So the peak is at -6 decibel. It even doesn't reach 0 decibel, in fact. Not a big problem for us. That's because we're having -3 decibel from the low pass, and from the high pass we're having -3 decibel, so a total of -6 at the cutoff. And the phase response at the cutoff is 0 degrees. That's because the low pass has -45 degrees phase shift, as we remember, and the high pass has +45 degrees phase shift, in total 0 degrees phase shift. As a result of this, if we want the resonance peak to occur at the cutoff, we should remove the inversion of the feedback. Because we already have 0 degrees phase shift here, we shouldn't invert the thing. The amount of feedback where the self-oscillation occurs is still 4. That's because we have -6 decibel approximately from each pair, -12 from both. Pretty much the same. I will now just demonstrate the sound. So this is a linear 4-pole band pass, or I can even show you the structure in the beginning, again killing the modular outputs. So just this feedback around 4 1-poles. These 1-poles are actually multi-modes. They have low pass and high pass outputs. So from the first one I'm picking the low pass signal, from the second one I'm picking the high pass signal, and so on. So the same as you have seen on this picture. And now we're going to play this. No resonance, and now we can add resonance. Again, self-oscillation almost. Again, it's internally clipped so it doesn't explode. Bandpass sound. How do we make an 8-pole one? We increase basically double the number of the filters in here, where we're getting different kind of sound, somewhat. There is one more difference because we're now having 4 of these pairs. The amplitude drop will be not -12 at the cutoff, but -24. That's already a lot. So we're compensating this thing a bit because it's now like really an audible drop in the volume. And simultaneously, this means that the self-oscillation will occur not at k equal to 4, but at k equal to 16. Because it's not -12 decibel, which we have to compensate, it's -24 decibel, which we need to compensate. Otherwise, it's pretty much the same. So very simple. And now we also want to make nonlinear versions of those, where simple feedback saturation is pretty straightforward. Transistor style raises certain questions because it's not immediately obvious how to generalize nonlinear transistor ladder structure, at least the low-pass transistor ladder structure, to a nonlinear version. There are some options, and they do not look immediately convincing. So in principle, one could analyze maybe the hardware low-pass, hardware high-pass ladder as one option, or one could investigate a little bit, trying out different ways how to make it nonlinear. We just didn't do it because we're here for bread and butter. And we're having an OTA style where making high-pass nonlinear one pole is relatively straightforward. So again, we made versions of 8-pole bandpass ladder with simple feedback saturation and with OTA style nonlinearities. I will play it to you. So this was a linear version. Now we're trying the nonlinear one with a feedback saturation. I will increase the resonance now. Again, we're having some kind of sweet spot. And this is the OTA style. Against the sweet spot with kind of complicated sound. I kind of like this sound. Yeah, so this is again nothing very special, very straightforward to make in Reactor. And now I would like to go many years back in history where I became interested in synthesizers. Really many years ago, I was reading a lot, especially on the internet, and I remember reading on one forum about a special way to use Minimoog, where somebody described that you can take the output signal of the Minimoog and plug it into the external input, and this way you make an external feedback around the Minimoog filter. And back then I didn't have any access to the Minimoog. I couldn't try it out. I had no idea what it would sound like, but I already knew the theory behind the Moog ladder filter. And then I thought, okay, in the Moog ladder filter, the feedback is negative, and probably by making external feedback, they make positive feedback, and that's why it sounds different. That was my theory back then, which I couldn't even try out, or I didn't try it out. And many years later, I was talking to Max Zagler and Mike Dalliet, who were creating Monarch back then. And they were also looking into this effect, and they told me that it's actually much more complicated than just positive feedback or whatever. And the positive feedback itself doesn't sound that interesting with the Moog filter. But I didn't know it back then, and anyway, the idea stuck with me that you can try filters outside of their standard range of settings, and one of the most obvious things to do would be to try inverting the resonance. Like instead of positive, do kind of negative resonance. And I was trying it every now and then, and I also wanted to try it with a specific filter. So now let's see what's happening. I will turn the resonance down. Now I will in the negative resonance mode. So I will now engage the negative resonance mode. This knob has a different scaling. It's operating 4 times as fast. And if you can see the value here, I don't know if everybody can read it. Currently it's 0, which was showing the amount of the resonance knob going to 1. So when it was set to 1, it was the self-oscillation point. Now instead you have to look at this value, so it will be -1 approximately here. So this is kind of the amount of the feedback just inverting the self-oscillating amount of feedback, so to speak. If we had plus 16, now it's going to be minus 16, so to speak. And I will switch now to the linear filter, so you can see better on the amplitude response. And there is hardly any resonance appearing here. There's some kind of flat plateau appearing, but no resonance. Strange. So let's increase the resonance further. And then we kind of see that there are two peaks occurring like at the sides of the passband of the filter instead of one. And in fact, the self-oscillation point is reached at the feedback amount minus 64. So we had self-oscillation in the positive range at plus 16. Now we need 4 times as much feedback. This is minus 64. I didn't try it with the linear version. I just used linear version so you can see the amplitude response nicely. I immediately tried with non-linear version. It was the most complicated one because it's giving the richest sound, and I wanted to hear how it sounds. So let's listen. Pretty complicated. So this is exactly the sound which I demonstrated to you in the beginning. This is the sound of this filter. And I think now we can together build a conjecture why it sounds like this. Because at least I explained to you the theory that this complicated pattern in the sweet spot of the filter is due to the input signal fighting with the resonance. And now we're having 2 different resonance frequencies and the input frequencies, and they're not harmonically related. So we have 3 signals fighting for the headroom, and their fighting produces a more complicated pattern. And this is what is responsible for this more complicated signal, most likely. So this is how this filter was created. It's part of spontaneous decisions to do some bread and butter theoretical model of what is out there, and partially some kind of wild experimentation, like trying negative resonance amount. That's not the end of the story, because there is one additional step which I would like to talk about. As we had these 2 resonance peaks, we thought it would be really nice to control the distance between these 2 peaks, kind of filter bandwidths. And can we really do that? It turned out that indeed we can, and I will now explain to you how we did it. Bandwidth control. So the bandpass ladder filter is built out of these low-pass, high-pass pairs, each of them making a kind of special 2-pole bandpass, where you can control only the cutoff, more or less, if both are set to the same cutoff value. A typical 2-pole bandpass, like the amplitude response of a typical 2-pole bandpass, looks like this. It has a resonance control additionally, and you can create a resonance peak like this, where the signal here, the amplitude response becomes higher and thinner in the middle. Or at low resonance, you can make the resonance like really low. Depending on how you define it, you can say you can make it less than 0. And then you get a very low amplitude response and it gets kind of wider. This is not what we're really interested in. We rather would like to change just the bandwidth of the filter, because here we're changing both the height and the bandwidth. So the width of the peak is changing with the resonance, but we have coupling between both. We can get rid of this coupling by dividing the output of the filter, or the input, doesn't matter, by the value at this peak. This will bring all peaks to 0 decibel, like this. So the resonance will now control the filter's bandwidth. At the high resonance, we will have like very narrow peak, like this, and at very small resonance, we'll get a very wide amplitude response, very wide peak like this. And maybe we could use this, maybe we could replace this low-pass, high-pass pairs in our ladder with this kind of 2-pole normalized band passes and have the bandwidth control this way. I'm saying maybe because we can't take this for granted. You should remember that it's not only the amplitude response which is defining the filter behavior, it's also the phase response. So if the phase response behaves nicely, this is going to work. If it doesn't behave nicely, we'll fail. Fortunately, it just so happens that for a normalized two-pole bandpass, the change of the amplitude response and of the phase response when we control this bandwidth, these changes are completely synchronized, like 100% synchronized to each other. This means that, for example, we have this point here on the amplitude response, and there is some phase response corresponding to this point. And now we increase the bandwidth, so this amplitude response point goes here. And the phase response at this point will be exactly the same as we had at this point before. So the phase response will move exactly by the same amount with this point. So it's really just the stretching and shrinking of frequency axis. That's the only effect of the bandwidth control. But the amplitude and phase response stay completely in sync. And this means that if we put this kind of filters as the core of our bandpass ladder, by changing synchronously their resonance, we're effectively just shrinking or stretching the frequency axis of the entire bandpass ladder. And this will just change the distance between the peaks. This is exactly what we wanted. And I will show it to you now in the linear version first. So we can increase the bandwidth, we can decrease it. And you're having, of course, this formant quality, formant type of sound from the two resonance peaks. So with a linear filter, we're quite lucky, and it's relatively simple. It's more complicated with a nonlinear filter. Why is that? Because if you think about how we're going to implement this typical two-pole bandpass filter, on this picture, is probably the most common structure how you would implement a two-pole bandpass. It is so-called state variable filter, very famous structure. I'm not going to explain to you details of this structure if you don't know, but the point is it obviously looks very different from low-pass and one-pole low-pass and one-pole high-passes connected in series. And if we try to embed any kind of nonlinear behavior into the structure, it will differ from the nonlinear behavior of the low-pass and high-pass connection pair. And maybe it would be even nice, although personally I'm not very sure of that, because the state variable filter is also very difficult to get nice nonlinear behavior of. But at any rate, it's going to be different, and would like to keep the same nonlinear behavior of the filter. Fortunately, there is another structure which, for the bandpass which you could use. It's a kind of a derivation of a Salin key. I think there is even such thing as a bandpass Salin key in hardware, but I'm not sure. I never tried to make a model of a bandpass Salin key. I just know how a low-pass Salin key block diagram would look like, and from this diagram you can derive this kind of bandpass filter in pretty simple way. So I'm referring to this as a Salin key bandpass. I don't know if it's exactly the same as a Salin key bandpass which we have in the hardware. So don't quote me on that. The idea is that we're having this low-pass, high-pass pair and the feedback around it. And I think now you can say, hey, but this is just a two-pole bandpass ladder. Yeah, it's like pretty much what we had before. It's just we're having only one pair in here. And it's indeed, it's just a two-pole bandpass ladder which makes this two-pole Salin key bandpass. And the amount of the feedback controls the resonance. And we can put additional normalization here, dividing the output by the height of the amplitude response. Actually, we have to divide it a bit stronger because we don't want 0 decibel peak, we want minus 6 decibel peak. But essentially, we're dividing by the peak of the amplitude response. And then we'll get the normalized bandpass response, this one, which we're looking for. But when k is equal to 0, there is no feedback at all. And it also happen that normalization coefficient here will be equal to 1. So in this case, we're getting exactly the same chain of low-pass, high-pass, unmodified inside our bandpass ladder filter. Which means we can just replace each low-pass, high-pass pair with this Salin key filter. And then at neutral bandwidth, we'll have exactly the same nonlinear behavior because we're keeping these two nonlinear filters exactly as they are. And there are, like all other signal paths, are blocked. And if we change the bandwidth, we are going to have some different sound. So this is exactly what is happening here. For example, this is an OTA style sound. And I can change the bandwidth. And you can hear that it sounds exactly the same as the first one. So the neutral bandwidth setting is exactly the same sound. This is exactly what we want to have. We didn't want to change the sound, which we already obtained. And this is how we reach this goal. This concludes the end of the story. I hope you enjoyed the journey. I hope you could kind of feel being with us as we were developing this filter, the decisions which we were taking, how we came to certain conclusions, why we took them. I also hope that I managed to give you a feeling, especially to those of you who are not engineers but musicians, that DSP is not necessarily a dry science. It's an art, I would say, in the same sense like music is an art. I would compare DSP theory in that sense to music theory, because I know lots of people, I have heard many times people say music theory is useless, nobody can tell you how to write music, and so on and so forth. But I would think that these people have a very special approach to the music theory, because in my opinion, music theory doesn't tell you how to write music. It's just giving you some reference points. It's like a map which you familiarize yourself with. You know, okay, this is how tonic sounds, this is how dominant sounds, this is how like a typical progression sounds. And then if you have something like this in your mind, you can immediately recognize it, and this is familiar territory for you, and then you know where you can go from this territory if like you want to go on a standard route, and you also know if you want to do something non-standard, you know exactly not to go the standard route. So it works kind of as a map for you, but you're still fully creative. You can write music from your heart. It's just a tool which you use, a tool which helps you. And in the same sense, DSP theory and DSP math is just a tool which you're using. So what I have been talking about today is exactly how we have been thinking about this filter. So we were not sitting down and writing lots of formulas and graphs and what have you. This is exactly the kind of decisions and thinking way which we were following. And the science was just used occasionally to compute some specific values or analyze why is the resonance happening here, how much of the feedback I need to reach self-oscillation, and so on. This is where the theory, or like what kind of amplitude response does this filter have? This is where the theory comes very useful. But it's not telling you what to do. You're completely free. You can be completely creative. And I hope I managed to give you a kind of taste of this creativity in the DSP. And before we go to the Q&A part of the talk, I would like to thank a number of people who were involved in the preparation of this talk. So it's not just me coming here spontaneously on stage. There are lots of people who worked to prepare this talk. And you can see their names here on this slide. And last but not least, I would like to thank the REAKTOR team who worked hard on making the release possible, which should now be out in a few days. Thank you for coming and for listening. So let's do Q&A now, which we're going to split in two parts. First, we're going to do more formal part, where I would stay on stage, and I would like to ask you to keep your questions focused on the topic of the talk, so DSP and REAKTOR, or music DSP in general. And if you're having any questions beyond that, for example, about work at Native Instruments and whatever, we will do a more informal part of the talk afterwards. And there are also other guys from Native Instruments present who will maybe be able to answer these questions better than me. So let's just start with the DSP part of the Q&A. Marco should have a microphone. I would ask you to speak into the microphone so we can record your questions. Are we having the microphone? Okay, so first question, please raise your hands. Whatever.
I observed that it took a lot of computing power, about 40% of your processor, and you took a very high sampling rate, I think 174 or so kilohertz. Is this necessary to demonstrate a high quality signal, or is it possible to reduce it for 44.1, or is it some model that doesn't influence the sound if you go with the resources a bit deeper, because it costs a lot of computing power, I think.
So it has to do with the quality, for one. So first I want to say that there is actually not that much computing power, it's a bit less. Lots of computing power is taken by the spectrum analyzer. So now it's a bit less. I think it's halved. 25, yeah. So this is one thing. The other thing has to do with a high sampling rate, and it has to do with the quality. Two things. One is the aliasing, which is created by nonlinearities. And the simplest way to fight the aliasing is increasing the sampling rate, of course. The other ways would be pretty complicated. You need special anti-aliasing algorithms, which are just, I think it's the cutting edge of the DSP. These algorithms are just popping up. And then in this model, I'm using the so-called, well, not so-called, but sometimes referred to as cheap way or approximate way of resolving nonlinearities. Because with nonlinear filters, there is no straightforward way usually to solve the respective equations. If the filters are linear, the math is very straightforward and you can do it exactly. If the filters are nonlinear, you get transcendental equations and you have to resort to various numerical approaches to solve them, if you want to solve them exactly. And in my experience, it doesn't make even sense to try to anti-alias the method which is used here. This is the cheap method. It's even not trying to properly solve the equation. It just takes kind of a first guess, something like one iteration of fixed point approach, something like that. And obviously, it sounds much better at higher sampling rates. We could try lower sampling rates if you want. I will switch to 44. It still sounds kind of similar. Let's make a comparison. But there are, like, for one, you're having slightly different levels, so it's even not completely matched, and I think the sound is also cleaner. So yes.
Yeah. So you think you can create new instruments with it? For example, there are a lot of preset instruments, and you can maybe replace a 4-pole filter with an 8-pole filter, and then make instruments. Do you have some idea how to use it, or is it just a theoretical model in the moment?
I think this is a very good candidate for blocks. We didn't, if you know what blocks is, so we're having this modular kind of toolkit in a classical sense, like a hardware modular toolkit in Reactor. Because this filter like is asking to being used in modular patching, at least like the one which I was focusing on. And you can use this in synthesizers. And if I'm not mistaken, I don't know, Dave Forrester, who has been working on TRK01, told me, because I sent him the version of the macro library earlier, just for him to, actually I didn't even send it to him, I sent it to another guy at Native and he forwarded it to Dave. And then Dave told me that he wanted to use one of the 8-pole ladders for TRK01. I don't know if he used it at the end or not. So yeah.
Thank
you. Basically, I had the same question, but it will be continuation of this question about like CPU consumption and DSP. So the problem I'm currently have with all these like modern synthesizer products, that they are very, very CPU intensive. Like you load something like 50. And for example, when I use machine, like I need like very low latency, something like 64, and then it starts to crack. But I have like really high-end PC, sort of laptop, Windows, but I think I have very mediocre audio unit. Will it help if I change to something better, or it's still processed like on a PC?
I think it can depend on the audio drivers. In my experience, with some hardware units, you can get cracked. The audio out, yeah. We're having crackless performance at the same settings where some other audio card would crackle. So, yeah, you can try this out. I don't know, but
so like changing audio unit will help so the situation.
You mean the audio card?
Yes.
It might help.
It might help. So
it definitely might help. Yeah.
Yeah, and like why this modern synthesizer, like even filters, I know, for example, in Ableton, they also have the stuff, like I'm not like in this theory that much, but they also emulating this, what you explain, and sometimes a filter like consumes 15%, 20% of the CPU. Like, are there so many calculations happening in background, emulating sort of an analog or something?
You can have to compute lots of things. Okay, so for one here, these filters are not really optimized out. They're mostly made to be readable, to be simple, so people can learn from the internal structures, simple understand them, so there are no optimizations done internally for one thing. But even if you do optimizations, depending on, for example, you can make a quite high-end model of particular analog piece, and you want to model lots of nonlinearities and other interactions happening in there, and this means you need to solve quite complicated numerical problem, which simply takes time. So if you want all this kind of complicated behavior, this costs CPU power, of course. In my experience, or in my opinion, not only in my opinion, like I have some colleagues which share this opinion, you typically want filters with this rich sound in monophonic patches, mostly because in polyphonic patches, this rich sound is just clashing between, you have clashes between the voices. So there is kind of this balance. If you want a very rich sound from the filter, most likely you want it monophonic anyway, and then you probably can tolerate higher CPU load from a filter.
Okay, thank you.
Is this working? Could we probably have a look into the nonlinear one-pole filters?
Sure.
Yeah, that would be interesting.
So maybe first we have to look into a linear filter, which would give us the basis. So this is the linear filter. It's just an integrator with a feedback, and there are low-pass and high-pass outputs. Actually, I'm having a copy of my book here. I could show you a block diagram. Maybe this would be kind of informative. Here it is. Give me a second. I'm not really used to this keyboard, sorry, so I'm a bit slow with it. Right, so here we are. So this could be a good picture, or maybe I'll go a little bit further. So this was a high pass, and I think we're having even a multi-mode picture here. So this is the book which I have been referring to, right? So here we're having a multi-mode one pole. This is basically an integrator with a negative feedback loop around it. The cutoff control is implicitly understood inside the integrator, so it's like you multiply by the cutoff amount in front of the integrator. It's not shown in this picture. And here you pick the low pass, and here you pick the high pass signal. And then I think I'm having a picture of the OTA nonlinearity here. Right, this one. So again, this is not the only nonlinearity which occurs in the OTA. This is the one which we think is important, we chose to emulate, and this is just a saturator in front of the integrator here. So now we can return back to reactor. This is just a linear one pole, so just a negative feedback around the integrator, which we have seen before. And now if we look into the OTA version, here is this additional saturator in front of the integrator.
Okay, so it's basically very similar to the nonlinear normal one, just that the distortion saturation is in every one pole by itself.
Exactly, but it also works differently, because when you're having the saturator inside the feedback, you can describe its effect like from preventing the filter from exploding in self-oscillation, roughly speaking. And in this case, it actually has an effect of cutoff modulation, so to speak. So the integrator is controlled by the high-pass signal, or by the difference of the output and the input. And if this difference now getting very large, it will be kind of clamped. And it's a bit like reducing the cutoff when this difference is large. So it's not about preventing the one pole from exploding. One pole doesn't resonate anyway. It's about having a particular kind of cutoff modulation depending on the signal level. And this is not the same as just controlling the cutoff from the outside. It's more complicated because each filter controls its cutoff depending on the output and the input. And you're also having this kind of complicated behavior in transistor nonlinearities, for example, although it's different, but the idea is the same. Depending on different signals in your filter, you get kind of changes of your cutoff. And you can even hear this. I don't know if I can make this easily audible. Maybe I will try with a low pass. Because sometimes this, you can even hear it pretty well. So this would be the OTA filter. And let's start with it. And I will now increase the drive. No, I think we can't hear this. Maybe with a higher. Maybe we can compare it to the nonlinearity in the feedback path. Because I had some settings where this was very obvious. I don't know if you can find them now. I think now you can hear that the cutoff is changing, yeah? So this is the effect.
So it was just self-oscillating now without any input?
No, it was with the input. Because without the input, I don't think you will be able to hear the cutoff variation so much. It's a sawtooth. All the time during the entire talk, it was just a sawtooth at fixed frequency going through the filter. And I was operating cutoff for the resonance or some controls.
Yeah, so first of all, thank you for taking questions and having this talk. Regarding nonlinearities as well, how far do you think this can go? For example, there's obviously some inconsistencies in voltage with analog circuits. So, for example, the railing in op amps and something like that, I think also has to be taken in consideration for emulating a filter. And also, how does this computing-wise compare to, say, a complete simulation of a circuit?
I think it's a very good question in the sense that, I mean, there are different opinions in regards to how far it should go. And some people say, yes, we have to emulate everything which is inside the hardware, and only then we can say that the digital has replaced the analog. I am in a slightly different camp. Well, you could definitely count me as a kind of analog freak, so I really do have an appreciation for hardware sound very much. But I don't think that we have to emulate everything, because there are effects which will have this appreciation for analog not for the sake of being exactly like an analog. There are certain musical qualities which analog has, and that's why we like it. And as an engineer, if you try to make, or if I would be trying to make a model of specific analog device, I would try to identify which particular effects are those which I think are musical, which are important. And then I would try to understand which parts of the circuit behavior are responsible for this kind of nonlinearity. For example, this cutoff modulation is a pretty well analyzed nonlinear effect. It's pretty well known. What is it coming from? Probably that's not the only source of the cutoff modulation. There might be more, but this is like a very prominent one, and this is definitely worth emulating. And then I might identify one or two of the effects. I would make a model, and then I would judge. I would compare it to analog and then listen. Does the analog model have some other musical things which I would still like to have in my digital model? And then I would try to understand, again, which specific leakages, nonlinear behavior, whatever is responsible for this thing, and try to implement those. As opposed to making a complete model of the circuit, I don't even know if this is feasible, because if you think about kind of analog simulation packages, they're again some approximate models of what is going on in analog components, and these models are only as good as people thought they need to simulate them. And this can be an infinite road, which you will never come to an end. But whether you will find anything useful on that road, you judge it by listening. So make a digital model, compare it to analog, and see if you're still missing out on something, and then you can continue the research. And if you think it's completely okay, then this is where you could stop, or you could even exaggerate the effects, which like were not as strong as in analog, but now in the digital world they have complete freedom of control over this. You can make model which exaggerates the effects which you like. And of course, there's also a very strong subjective element, because depending on your musical preferences, on your musical taste, some engineer would think, I don't care about this effect, I don't think it's musical at all. Or maybe depending on the type of music or the type of sounds or aesthetics which you're into. And some other engineers will say, this is exactly the effect which I'm looking to. It has to be emulated no matter what. So it's an art. It's all up to you to decide. I don't think you can really make an exact model of analog ever. It's just infinite road. I'm not sure it makes sense to make automated models, just kind of use some kind of analysis package and draw the circuit there and use whatever coming out of that. I mean, it can be a nice thing if it works with a reasonable CPU and you get nice sounds, sure, why not? But if I'm building some model as an engineer, I might use this as a reference, but this is not something which I would be specifically targeting, because I would be targeting musical effects and not an exact emulation of something. But it's all subjective, like it's all up to you, it's an art.
Thanks.
Yeah, thank you. I have two questions. The first, if I look on your circuits, I was wondering if the wires could be like in a circuit, so that it's more visible where it starts or where it goes from. If they go over models, it's if it's too much models, it's getting complicated. Are there plans making this better?
Well, this is a standard GUI of Reactor, so to speak. And the wires usually actually do not come over the modules. Normally they look like that, for one. Only when I select a module, you have wires going over the modules. Of course, there's additional clutter from these duplicate wires in this case, but you have to realize that this is a ZDF toolkit. This is not a standard feature of REAKTOR Core, so to speak. This is something which is shipped with a macro library. We just have seen this possibility. So we can make a set of macros which allows you to easily build together ZDF filters. And yeah, unfortunately, we have to deal with these two wires. Here, we had ideas how to make it possible only with one wire, but that required a very significant extension of the language. So REAKTOR Core is a graphical language. And would be a very significant investment just to get that specific feature possible. So at that point, we just said, no, we're not doing it right now. Anything is possible in the future. I can't tell you what is going to happen.
Okay. Second question is about multi-threading. What's the concept of Reactor? We have heard from some others here that there, if you want high quality, you have also high CPU consumption. Is there ways to reduce it by multi-threading?
At the moment, Reactor itself doesn't support multi-threading. You can use multi-threading as it is supposed by your host. So if you plug several Reactor instances, then each one can potentially run a different thread if your host does this. As to whether multi-threading will be supported natively in Reactor, I can't tell you at the moment. Obviously, it isn't supported. Whether it will be supported in the future, there are large conceptual problems because Reactor is a very open system. You can connect lots of things together. And having some kind of automatic hidden under the hood communication between different threads where all this inter-thread latency, communication latency is involved and whatever, I don't know if it's even possible. Maybe it's possible, but off the top of my head, I have no idea. So it's a pretty challenging subject.
Everybody loves the sound of analog filters, so it really makes sense to replicate them in the digital world, but aren't there any truly unique digital filters out there where you can make things which are simply not possible in the analog world? Or is it simply we're still trying to generate what our ancestors did? And sorry, this is no criticism, but I'm just thinking about why. I mean, you have so much possibilities in the digital world. I mean, you can.
I have no idea if the filter which I demonstrated to you today exists in the analog world. Is that an answer?
But it's somehow related to something.
Oh,
which
yes,
is-
it's related because I think we can learn a lot from the analog world. There are lots of things which are already sounding good for granted. But what was done in this filter is already a further extension of this. And in my personal opinion, this is one of the main roads which we should go digital filter-wise. So, and this also why I wrote that book, The Art of VA Filter Design, which I mentioned. This book is not about how to make models of existing analog hardware. It even doesn't deal much with the analog circuit at all, but rather tries to derive generic principles out of analog circuits. And in a sense, this is a way to build digital filters which have similar qualities to analog. But you can just take this approach and build new filters. And the filter which I showed to you, I think, is one example of that. Yeah, probably doesn't go very far. You still can look back and see the analog world behind you. But I think this is some steps in that direction.
Okay, thanks.
Is a comp filter?
Can you speak into the microphone, please?
Just continuing this question, the comp filter is the typical digital filter, or there is an analog version of this? Or it's not a filter at all?
Oh, it is a filter? Well, it's not a differential filter in the sense, so it's like a different filter from the majority of the filters. There are obviously analog models of the comp filter. You have analog flangers using brigade bucket delays or whatever, and the first flangers were made from tapes. So yes, you do have these filters in analog world, and you also can emulate certain qualities which you like of this filter. Yes, for sure.
All right.
So Vadim, thanks a lot for your great talk. Any further question, or you can talk to Vadim in the informal part afterwards. And do you have some recommendation for the students when they start to get into the world of DSP? Some considerations or something what you think it is really important that they should know when they go into this world?
If we're talking about the DSP science, then in my opinion, it's quite unfortunate for the music DSP field. Music DSP field is like a very narrow, very small portion of DSP out there. And in my opinion, it's quite unfortunate that music DSP was developed very much in this mainstream DSP paradigm. And lots of things are not very well suited for the music DSP needs there. For example, I can see on the forums regularly people asking questions, how do I make my filter respond nicely to the cutoff modulation? This is one of the most common questions, possibly the most common problems of the beginnings. The answer is don't read classical DSP texts. It was actually the main motivation for me to write my book, which I mentioned, because I believe that music DSP should be taught. I mean, that's my personal opinion, of course. I'm not trying to say that other opinions are wrong. I'm just expressing my opinion now. That the music DSP needs to be taught in a different way, especially regarding the filters. And that's why the book was written about the filters. And I tried to create some kind of didactical path how one can learn the filters from the angle which is immediately usable in the music DSP context. So if you have read classical DSP text and try to read my book, maybe you would be angry or would have some problems, because it's really addressing everything from completely different angle. But it's just my personal belief that this angle works very nicely for music DSP. So this is one thing which I could recommend. So don't learn classical DSP way to build filters. Learn the way which is used in virtual analog world. And now we have this kind of almost hype word, zero delay feedback filters. This is the thing which operates nicely and doesn't create problems. This is one of the major pitfalls, for the beginners, I think. And as generally talking about DSP, and also for those who are not on the engineering side, but more experimental, creative side, I just remember a joke, advice for beginners, begin. Just begin experimenting, try out, get familiar with this stuff, and then you will see what you like, what you don't like. Look what's out there. Yeah.
Thanks a lot, Vadim.